So imagine you are given, or you derive from the analysis of a recursive algorithm, some complexity function. So this is just a function that represents the number of operations that occur in some scenario, just for our discussion. It may be a recurrence relation, which again is a recursive way of describing a function to somebody, just to keep it simple. So oftentimes what happens is you get descriptions of some function in a way that's quite a lot like our examples we've seen before. So let me give you an example of what I'm talking about. This is going to be a little contrived of an example at first. So suppose I were to give you this function. It looks like this. For n is greater than 1, where t of 1 is equal to c1, where c1 is some positive integer. So suppose that you're given this complexity function, just for the sake of our discussion here. Notice that it has a recursively defined part, namely this part of the definition, and then it has a base case. So an intuitive way of talking about a recurrence relation like this is you imagine like you're collecting up the non-recursive parts of the quantity. So notice that kind of like some of the examples we have a recursive part, then we add 1. But notice that if I look at every one of these calls here, each one of the recursive cases, each one will include adding 1 every single time. I can imagine I go around collecting up for each one of these calls on a smaller input. It's like collecting up the plus 1s, right? It's like I'm collecting up the waste of all of these calls. Just akin to running through and executing this, just like if it were like the recursive algorithm that it represents for its execution. So each one of the calls produces me a plus 1 until I hit a base case for which I get the C1. So an intuition I want to give you for when we deal with very simple recurrence relations like this one is you can think of it like I'm collecting up the non-recursive work, and I'm collecting those up into a basket, and I want to know how many things are in the basket when I reach the base case. So I would like to derive a relationship that doesn't have any of this recursive stuff in it. And that's what we refer to as solving the recurrence relation. I would like a way of describing the function t without needing to describe it recursively. I would like what so-called we would call a closed form expression. So just to keep it simple for our example here, I'm just going to get rid of the plus 1, even though it wouldn't be possible to have an algorithm that does this scenario, because your algorithm will have to perform at least one operation before it does a function call, right? Doing the function call is at least one operation. So I must stress that this is just meant to illustrate the principle I'm going to talk to you about collecting up the non-recursive work of each call. So we're going to use so-called repeated substitution or iterative substitution. These are two names for the same thing generally, or some people call it solving by iteration. We're going to use this technique in the scenario for this example. We'll also do another one, and then we'll see how we can check it. So to apply repeated substitution or iteration, we write out write out the definition of T of n, then T of n minus 1. Because remember, it recursively calls on T of n minus 1, right? And T of n minus 1 will call on T of n minus 2. Then T of n minus 2, and so on. And determine how T of n, or how T is computed by writing out a sequence of equations, and finding a pattern. So we're going to try finding a pattern. A good guess. We're good. As humans, we're very obsessed with finding patterns in almost anything. The unfortunate thing is just finding a pattern doesn't mean you found the correct pattern, okay? There could be several correct patterns, but most certainly you can't just say, oh, well, I noticed this pattern, but it doesn't mean it's true always, okay? Especially when we're dealing with the M word, you have to be a bit more careful about it. So, for example, I'm going to write down a bunch of equations so that we can use them. Well, T of n is equal to T of n minus 1, right? And T of n minus 1, that's equal to T of n minus 2, right? And T of n minus 2 is equal to T of n minus 3, and so on. I could keep writing down more equations. And T of 2 is equal to T of 1. And T of 1 is equal to C1. Now, if you're algebraically inclined, you might look at this very quickly and see how I could express T of n. But just for the sake of our discussion, I'm going to go through this carefully. So I want to illustrate the technique. So substitute. So what we're gonna do is we're gonna try substituting each of these equations into each other. Namely, we're gonna start at T1 and work our way up to T of n. Now I must stress that you can work bottom up or top down in this process. I find when you have a recurrence relation like this, you might start at the bottom and work your way up. I find that tends to work pretty decently. But I want to bring the intuition I had with collecting up the non-recursive work into this, just to help you visualize this. Substitute T of 1 into T of 2. Then T of 2 into T of 3. And so you imagine when I have T of n, every time I call on one of these recursive calls, right? I have a recursive call plus some non-recursive work. I can imagine I'm collecting up all that non-recursive work that happens with each one of those calls, plus the initial definitions, the base steps. So I'm going to start off with the base step just to illustrate my point. So T of 2 is just T of 1, right? T of 1 that's just C1. This is what T of 1 is. So when I'm working my way up from T of 1, this is like if I had my bucket here. I'm going to collect up all that non-recursive work. This is C1 right here. This is C1. I put in the bucket. So far I have C1 in here. So now, let's try putting now T of 2 into T of 3. Well, it says that T of 3 is just C1, right? Because that's just what T of 2 is. Right? I have no there's no non-recursive work on this guy, right? There's none. I'm not adding anything into the bin. T1 did, but that's it. So same thing. This is C1. That's just T of 3, right? And I can keep doing this. So I have T of n minus 1 is equal to C1 because that's what T of n minus 2 is. And finally, I could substitute T of n minus 1 back in. I have T of n is just C1 because that's T of n minus 1. So notice that the total amount of non-recursive work that happens just ends up being what was introduced in the base case, C1. That's how it's totaled up. And you see it's exactly right here. So since C1 is a positive integer, and T of n is C1, what does that mean? T is big O of 1. So notice in this case, we only collected up work from the base case. Nothing from any of the other cases, right? So that means that this, if you gave me an algorithm with this, now keep in mind, we already talked about that you wouldn't have an algorithm that does this, right? It would never. Now I must stress that the only way this would even work is if you had it where it just executes the base case. Because the recursive case just simply it doesn't make a whole lot of sense to have it where it doesn't have any non-recursive work. But my point stands is that if you gave me that recurrence relation, which I must stress does not have to represent the running time of an algorithm, it's just a function, right? It is big O of 1. So you can take our idea and extend this further if we wanted to. So let's do something a little bit more advanced. Now, do you notice that if I were to have it where we had our first example where I had the +1 before I got rid of it, notice that every time I had one of our equations, it would have added 1 to the bucket each time. So it'd be quite natural to expect that in that case, you should anticipate that each equation contributes something that's a positive integer amount of work every single time you do a call, and there's a linear number of them. So instead of a constant, you might expect something else. I'll let you think about that. So just go through the same example, but instead introduce the +1 that occurs each time. So let's go through another example. So just keep that in the back of your mind with this next example. So the whole idea with iterative substitution or iteration is that we write down a sequence of equations that we hopefully know the conditions for which the base case occurs, so that we have a whole definition of how we compute our function for a given input. And then what we do is we try to substitute by repeatedly applying the definition of each function to each successively smaller part of it, so that we try to gauge and develop a pattern that includes no recursion at the end. So we could do it again from the top, like if you want to start with T of n, like for example from here, you could have seen that I just said, okay, T of n is equal, okay, if that's equal to this, then that's equal to that, then that's, okay, well notice that T of n is equal to T of 1, which is equal to this. So just, I didn't need to go much further than that, right? You also could have worked your top down by just identifying when T of n is equal to T, like when do you actually call T of 1 and how many equations are between there? But you'll notice very quickly that there is nothing else happening except just these calls, right? The point is that you got to think carefully about it case by case, but most certainly you'll find that bottom up or top down, it's sort of analogous to thinking about things recursively like we discussed. Okay, let's do our next example. So this one will actually have stuff that's going to go in the buckets, okay? So consider Gn, or it is g of n minus 1 plus 2n. So this should remind you a little bit of what we had before. I made it a little bit tougher. This is for n is greater than 0, where, let's go with g. I was about to write t, where g of 0 is equal to 1. So we're going to go through the same process, just I really want to illustrate this idea of collecting up the non-recursive work into a bucket, but we all know how that happens, the pattern for which you collect up the garbage, okay? So we apply iterative substitution where we will write equations for g of n, then g of n minus 1, then g of n minus 2, and so on, to find a pattern. So we're going to go through the same process again. So it's usually a good idea to write down these equations, regardless if you're working up or down. That way we have the equations, they exist, at least in a M-word sense, okay? So g of n is g of n minus 1 plus 2n, right? So what's g of n minus 1 then? So we had another equation for g of n minus 1. Well, everywhere where I had n, you have n minus 1. So this is going to be now 1 less. So we have g of n minus 2 plus 2. Remember, it's now everywhere you've seen n is n minus 1. And so on. So g of n minus 2 is going to be 2 less. This would be g of n minus 3 plus 2 times n minus 2. So wherever you had the n, you put in whatever that input is. And so on. Until you get the g of 1, which is going to be equal to g of 0 plus 2 times 1. And then we have g of 0 is equal to 1. So when you stare at this, you realize, okay, every time I apply this recursive definition, every time I'm adding something, it looks roughly linear each time, right? So that's a good intuition for where we're going here. So if I start down here, for example, like I did last time, notice every single time when I introduce something into my bucket, notice that every time I start with 1, I put 1 in there, and then I put in whatever that number is times 2, right? Then every time I apply each one of these, whenever I substitute the next equation back in, it's whatever the thing is times 2 I add to the bucket until eventually I get up to g of n. Does everybody understand the main idea? So the whole idea is I want to know how garbage is putting in my bucket, okay? That's what I want to know. That's all I want to know. So let's go through the same process again. Let us substitute the equation for g of 0 into g of 1. Into g of 1. Keep going. Into g of 1. Then g of 1 into g of 2, and we get as follows. So g of 1 is equal to 1, which that is just the definition of g of 0, plus 2 times 1, right? Remember, it's 2 times the something. As long as you remember it's 2 times the something we add into the bucket every time, it's going to be a piece of cake. But what's g of 2? G of 2 is just 1 plus 2 times 1. That's what g of 1 is. You notice I'm just writing it, but there is a little bit of an art to the way I'm expressing this, because you want to try to identify a pattern as you keep applying each of these based on the intuition you got from over there from writing out the equations. But what is this being added to? What I add to the bucket, because remember I added 2 times 1 beyond that in g of 1, right? So now I have 2 times the something, which is 2 times 2, right? So what is this actually? This is 1 plus 2 times 1 plus 2 times 2. Do you see anything interesting happening here? Well, let's do it. Let's keep going. Let's keep going. Then, now let's substitute g of 2 into g of 3 and g of 3 into g of 4 to see a general pattern. Remember, I'm just trying to guess it. I have to be very careful because if I get it wrong, I may that's not good, right? This is why we would check our guess once we're done with it to see a general pattern. So what's g of 3? G of 3, well, we established that that's 1 plus 2 times 1 plus 2 times 2. Well, that's just g of 2 plus 2 times the something, right? Well, what's that? That's 1 plus 2 times, well, because it's 2 times the 1, 2 times 2, plus 2 times 3, right? This is the same as me writing 1 plus 2 times all of this, 1 plus 2 plus 3. Do you see a pattern arising here? Well, let's do another one. G of 4. This would be 1 plus 2 times 1 plus 2 plus 3. This all is g of 3. Do you see how I'm just substituting in where g of 3 would be with what I currently have? And this is the pattern that I'm guessing. This is the iterative aspect of this, or repeated part. So remember, it's 2 times the something, but that's just 1 plus 2 times 1 plus 2 plus 3 plus 4, right? Do you see a general expression yet? Does it stick out to you quite yet? Well, let's keep going. So now let's try to give some general expressions. So imagine you keep substituting. So dot, 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 we get to g of n minus 1. Well, what would have been the good guess for this? Well, it's 1 plus a something. It's 2 times 1 plus 2 plus 3 plus all the way up to whatever the thing is, because where did it end? It went up to 1 less than that inside these parentheses, right? So it's n minus 2 right here. So that closes this, that closes that. We need, there we go. So this is g of n minus 2 plus 2 times the something, right? But that's just simply 1 plus 2 times 1 plus 2 plus all the way up to n minus 1. Now, do you see a general pattern now? Does it stick out like a sore thumb now? What was I doing? I was just, remember, every time I took my bucket, I apply one of these equations when I do the substitution. It is just 1 plus 2 times whatever the something is for the input of the equation, right? So each one of them starts at n and works its way down to 1. So naturally, if you start from 1 and you work your way up, it should look something like this, right? It should be 1 plus 2 times 1 plus 2 plus 3 plus all the way up to n, right? Now let's simplify. So now this is my guess. This is what my guess is based on using repeated substitution or iterative substitution. So simplifying g of n, or g, we obtain the following. Well, g of n is equal to 1 plus 2 times 1 plus 2 plus 3 all the way up to n. But what is this? What is this? I can rewrite this using a summation. 1 plus 2 times the sum from I is equal to 1 to n of I. So notice that this is 1 plus 2 plus 3 plus 4 all the way up to plus n. So it substitutes each value of I with each one of the terms here. But here's the thing, that has a closed form expression, This is an arithmetic series right here. There's a nice closed form for this. Namely, it'll look like this. N times n plus 1 divided by 2. But notice that this is 2 times half, right? So those two cancel and annihilate each other out. So I end up with 1 plus n times n plus 1. But this is equal to n squared plus n plus 1. But what is that in terms of big O? That's big O of n squared, which matches the intuition we had at the beginning of the example. So we had to double check using our analysis here. I'll say which is. I was about to say where is. Which is big O of n squared. Completing the example. So that's iterative substitution. Now, just as our important remark is that, remember, we're deriving it based on the pattern we're observing, right? We still, if you really just need the check, that requires you to prove something, okay?